All right. Hello, everyone. Welcome to class. So today we're starting a pretty different chapter from the Stewart textbook. We're starting chapter 11, and precisely we're going to study 11.1, okay? 11.1, and that's sequences. Okay, so I need to say this up front that this chapter actually lays the foundation for a lot of things we're going to do in chapter 11, okay? And even throughout this class, okay? So this is the last chapter we have to study in this class. So we'll go up until 11.11 from the Stewart textbook. Okay, so we're starting here to lay the foundation, and I'd like you guys to, really pay attention to this. I like you guys to pay attention to the details. All right, so let us start from, from step one, and we keep growing that way. Now let's start by definition, okay? So we're going to see a lot of definitions and a couple of theorems as well to help us in some areas. So definition, a sequence is a list of numbers. A sequence is a list of numbers written in a specific order. Okay, a sequence is a list of numbers written in a specific order. Now, an example of such is, let's have first term A1, A2, A3. I can continue on and on until I get like A50, right? I can as well continue again. I get to AN, right? And I can go forever. Now, this kind of list is endless. Okay, so that means I can keep going and going and going forever. Now, what can I identify? This first guy here is what we call the first term, because it's the first guy on the block, right? So this guy is just the second term. So we can keep moving. This guy is the 50th term. Okay, and this guy is what we call the nth term. Okay, the nth term, we're going to do a lot about, the nth term as we move on. Okay, remember the list is endless. Okay, so let me just state that the sequences that we intend to study, the sequence that we intend to study are infinite sequences. Okay, so we're intending to study such kind of endless behavior. Okay. Okay, so what does that mean? So AN is followed by A sub n plus 1. Now, what does that mean? Let me explain what that means. So remember, we have A1. After A1, the next term is like A2, right? A2 is just A1 plus 1. Now, if I continue this list and I get up to AN, remember there's a plus 1 that's coming in. So that means the next guy is AN plus 1. Make sense? All right. Okay, so now there's actually a compact way to write this guy, all right? So the sequence, let me write the sequence A1, A2, on and on. We can denote this guy in terms of notation. You have A sub n, something like this, okay? For the infinite sequence. Or if you don't want to write it like this, you can write it AN, where your n is going from 1 to what? Infinity, okay? It doesn't end. Such an endless list. Now, I need to mention at this point that oftentimes we can define sequences by giving a formula for their terms. Okay, so an example, let me explain what I mean. So sequences are most often defined. Sequences are most often defined by giving a formula for the terms. What does this mean? A first example. Now, if I have a sequence, this guy, of course, this is infinite. I can put n from 1 to infinity. This is infinite. What does this mean? Okay, this means that your nth term is going to be n over n plus 1. Okay, your nth term, that's more like the nth position. What do you have on the nth position? If I ask you for your first term here, you just do a1. Okay, that's when n equals 1. But the nth term is when n is n itself. All right, so now if the nth term is this guy, so what does that mean? This guy is going to give us, plug in when n is 1, remember you have 1/2. Now this guy says n is going from 1. When n is 2, what do you have? You have 2/3. When n is 3, what happens? You have a 3/4. I keep on going on and on until I get to this nth position. And this is going to be n over n plus 1. And I can go on and on because this is an infinite sequence. Okay? And this is an infinite sequence, and we treat infinite sequences specially. Okay, I'm going to need this screenshot. So let me just keep pulling it down up until the point where I'm going to use them. All right, so example 1. And another example on this guy, let me call it example 2. Now, if I have like an alternating sequence, alternating sequence means that the signs are changing. Okay, so think about let's say you have a -1, 1, -1, 1. It keeps going that manner. That means the signs keep changing. Okay, so n minus 3. N is going from 3 to infinity. Now, of course, this index has to make sense, right? Suppose this index is n is going from 1, then there's going to be a problem because you have 1 minus 3, that's a -2. -2 within a square root is a complex number, so we don't want that, okay? So even at the level of the indexing, it all has to make sense. So this actually means that what? What is the n term? Can you tell me, guys? An, right? -1 to the power of n, then you have the square root of n minus 3. Now, what will this guy generate? Now, let's see. When n is 3, what happens? Plug in 3 here. You have -1 to the third power, and then you have 3 minus 3. Oh, obviously, you got a 0. When n equals 4, what happens? You have a 1. If you continue in that manner, you have a square root of 3, negative square root of 4. It keeps going on and on. And then you have the nth term, and it's even endless. Now, in this case, this 0 corresponds to your first term, okay? So first term, the idea of first term is not just all about when n is 1. It's like the first, what's the first guy on the block, okay? So that becomes our interest, the first guy on the block. So let me move my screenshots a little bit further down because I need them at some point to make, some explicit explanations. Okay, so let's keep working, okay? Now, let me give you guys another example. Now, if I give you a list of numbers and I ask you to find the formula which generates that, okay, I can give you a list of, okay, so let's say find a formula for the general term an of the sequence 3/2 negative 5 over 4, 7 over 8, negative 9 over 16, 11 over 32. Of course, it's infinite, right? So that means I have to put these 3 dots. That means to show that it goes on and on. Now, my concern again is to find a formula that produces this guy, which is pretty much like what is the nth term. Okay, so the nth term is like the A of n that we write is like the generator. Okay, which tells you when you plug in a certain number, you get this and that. Okay. There are a few things to check, okay, when you want to do this, because you do it based on your intuition, right? So the first thing to do is you want to identify what is the first term. Okay, the first term is 3/2. The second term is negative 5 over 4. The third term is 7 over 8. The fourth term is negative 9 over 16. What is the fifth term? The fifth term is 11 over 32. Of course, on and on, right? Now, but what did you notice, guys? We noticed that, did you find out that we have alternating signs? The first term is positive, second term is negative, third term is positive, fourth term is negative. Now, whenever you have alternating signs, it means that there's an inclusion of, it could be negative 1 to the power of n. It could be negative 1 to the power of n plus 1. It could be negative 1 to the power of 2n. No, 2n is going to make it strictly positive for all times. So it's not going to be 2n. But it can actually be, yeah, you can have like 2n plus 1. Yeah. You could have, say, negative 1 to the, let's see, n minus 1. Yes, we can have something like this. Okay, so it all depends, right? So, but these are just some random types of alternating series, generator that you find, right? So now it has to be one of these, or maybe pretty much one of these equivalents, okay? But let us see, we'll soon discover which one is actually the correct one. Let us see. Okay, so first thing, you see what we're talking about, guys. I splitted out the terms, then I'm trying to just explain that, okay, these are kind of things that gives you indication of which one you can use. Okay, so let's pay attention because we do this by intuition. Now, did you take note of the bottom? Can you guys take a look at the denominator? You have a 2 on the bottom, 4, 8, 16, 32. They are all even numbers, right? Okay, so what you have on the bottom, they are even numbers. And what else do you discover? You find out that there's this sort of power of 2 that works with them. Okay, so this is 2, this is 4, this is 8, this is 16. What comes to mind, guys? Okay, so that means that the pattern on the denominator seems to have this kind of 2, 4, 8, 16, 32, on and on. So what can I notice, guys? This means that this is kind of like 2 to the power of something. Because this guy, the first guy here, corresponds to the first term. So this is like 2 to the power of 1. What about this guy? 2 to the power of 2. What about this guy? 2 to the power of 3. What about this guy? 2 to the power of 4. What about this guy? 2 to the power of 5. If we have the next guy here, I can tell you it's going to be 2 to the power of 6, because it has to be the same order. Now, what do I notice? I notice that this guy, I can just put it as 2 to the power of n, where your n is actually from 1, okay? So let me write this better. Where n is 1, 2, blah, 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 blah. Okay, so that's the first part. That's the bottom. What about the top? Now let us even pick the top again. Okay, so I'm taking it as slow as this so that everybody sees what is going on. Again, let me move my definitions. I need them, so it's just unfortunate that I have to keep moving it down and down and down until it gives me more space to do my work. So let's keep moving it down. I go down. Okay, so I hope I don't move it down after this and then use it. Okay, so let's get back here. So what about the top, the numerator? What you discover about the numerator? Now, at this moment, we have negatives, right? On the top, we have negative guys. Okay, so that means there's a presence of a, let me come here and say -1 to the power of something. But now I just want to pretend as if there's no negative sign first. 3, 5, 7, 9, 11, and it keeps going. Now, what do you notice, guys? The difference between this guy and this guy, the distance is 2. The difference between this guy and this guy is 2. The difference between this guy and this guy is 2. The difference between this guy and this guy is 2. Okay? So remember, this guy corresponds to the first term. So think about it. What is 3 itself? 3 is 2 plus 1. Okay, so what is this guy? Let me write it the other way around. Let me write 1 plus 2 so that you guys can see what's going on. It's like 1 plus 2. This guy, what is 5? 5 is 3 plus 2, right? What is 7? 7 is 5 plus 2. Now, in actual fact, that means that this guy, in terms of writing it in terms of n, that means it's going to be like 2n plus 1. Okay, so at this level now, we'll pretend as if, for those of you who have understanding of AP and GP, it can really help you here. AP is just arithmetic progression, and then GP is geometric progression. Okay, so AP is arithmetic progression, GP is geometric progression. All right. So this is 2n plus 1, but right here now I'm pretending as if I don't know all of those and just do it based on intuition so that you guys can actually follow. All right. So numerator, this is the guy. So we have something like 2n plus 1. But I still have a concern, guys. The signs are changing. Okay. So the first sign is positive. Okay. Positive, negative, positive, negative, and on and on. And we said this guy has to be a kind of -1 to the power of something. But remember, this is when n corresponds to 1. The first term here is when n equals to 1. If I do -1 to the power of n, when n is 1, there's a problem. -1 to the power of 1 is a -1. But what if I add a 1 to it? -1 squared, what does it give me? +1. So that means this guy has to be n plus 1. Okay. Actually went slowly so that you guys can see what is going on. -1 to the power of n plus 1. So now I have to put things together. Okay, so if I put them together, I can now say thus a sub n is going to be -1 to the power of n plus 1, and then 2n plus 1 divided by 2 to the power of n. So this is going to be my formula, where your n is from 1 and it keeps moving. Okay, make sense? Now to a particular definition that I need. Another definition. Now, sometimes the most interesting thing that happens to these guys are pretty much what happens in the end. Okay, so pretty much it's like the most important thing that happens, what happens in the end. So that will lead us to convergent sequences. Okay, so sometimes towards the end, they all contrast on the bottom. Towards the end, they can actually approach a certain number, or they can approach a certain value. Okay, they can approach a certain number or a certain value. So that leads us to the idea of convergent sequences. Okay. Definition. Convergent sequences. Okay. So now when is a sequence set to converge, or when is a sequence set to have a limit? I mean, this is now the point where I need this guy. All right, so a sequence, you have a sequence A sub n. A sequence has a limit when we can actually write it as this guy, okay? Or pretty much in terms of this way. This is another definition, but for the purpose of this class, we're going to use this first definition more, okay? All right, so if we make the terms, if we make the terms closer, close to a certain limit, as n goes large, what happens? Then that means this guy, if you see, can you see this guy? Say if we make the terms an as close to L as we like by taking n sufficiently large, that's what this guy means. Okay, if this limit exists, then we see the sequence converges. So now, if we want to put it together in terms of definition, a sequence is said to converge when the limit of that sequence exists. Make sense? Okay, so if we have a convergent sequence, then what happens to the limits? The limits exist. Okay. Right. So now let's look at an example. The sequence, this guy is convergent. Now, if I want to check if it is convergent, now it tells me it is convergent. What do I need to do? Just find the limits. Okay. So what is the limit of, what is an here? An is just 1 over n. So that means limit as n goes large of 1 over n. Now, what is this limit, guys? This is just 0. Okay. So what kind of number is 0? 0 is a finite number, and that means it converges. All right, so here in this session, you need to remember what you learned in about computing limits, okay? You need to have a good idea about your limits, limit computations. So another example, the sequence got a mistake right here. This guy, this sequence is divergent. Now, what does it mean if the sequence diverges? That means the limit of that sequence does not exist. Okay, so solution, limit as n goes large. What is the an in this case? That is -1 to the power of n. I mean, but this limit depends on the value of n. Okay, when n is even, then it converges to 1. When n is odd, it converges to -1. So that means this limit oscillates or alternates between -1 and 1. So because we don't have a single value, what happened, guys? It diverges. Okay, limit of this guy alternates. So let me write it this way, alternates between -1 and 1. So we cannot have all the terms becoming arbitrarily close, to a single value. Now, the idea of convergence is that, just as I said earlier on, they are moving compactly to the same number. Okay, so I'm using the word compactly in a loose sense now. They are approaching a certain value. If you look at the first guy we saw, the first guy we actually saw was about 1/n, right? Okay, let me say a little bit more. Now, if I want to pull out this list, okay, so this list is like 1/2, 1/3, 1/4, 1/5, on and on. As I keep moving, as n keeps increasing, okay, as n keeps increasing, what happens? This number becomes smaller and smaller and smaller and smaller and smaller until it goes towards 0. Okay, so that means as my value of n keeps going large, when n becomes 1 million, okay, so that means you have 1 divided by 1 million. That's like a 0.0000 something, right? So that means it approaches 0. Okay, but in the second case, it's difficult to tell if it really approaches 1 or -1. So it doesn't go towards a certain, just a single value. It now depends on the value of n. So we don't like that. So that means it diverges. Okay, so this is just a definition here just to corroborate this last example that tells us when we have some sort of divergence. Okay, so I'm not going to say a lot about that right now. So this is another theorem that is going to come in handy. This theorem is going to come in handy very soon. Okay, so this is a definition. Okay, so now I think I'm free to talk about this theorem at this point. Okay, so theorem. Okay, this is another theorem. Let me just expand it better, guys. Okay. Now, the first theorem is this. Let me explain what these guys are saying. Okay. Now, the first one is telling us that if I have the limits, right? The limit of a function. Okay, let me just write this so I can. Yes. Now, this guy says that if the limit of a function, right, of f of x as x goes large, if the limit of this function is L is a number, right? And if this guy, f of n, if this guy produces the sequence, then this is true. And the best way to see how this works is when we do examples, okay? So right now it still looks like theory, but when we do an example, you see how applicable it is. That if you have a function and a sequence, and if the limit of that function approaches a certain number, all right? So, and if the function with the function of the nth term, or if the f of n, right? When you plug in n, if it gives you the sequence, then that means that the limit of that sequence is the same thing as the limit of that function. Okay, so it's such a powerful tool. It's a powerful tool which it's very nice to use and to work with. Okay. Right. So the theorem. So this is another theorem, just like we talk about limit of loss of indices, I mean, loss of logarithms. So we also have loss of limit loss for sequences. That means what kind of operation are permissible in the level of sequences, okay? So the first one is this guy. Okay, so if I have the limit of the sum of two sequences, that can be splitted down, or I mean splitted out, okay? That means I can split them out. Okay, if I have the limit of the, an minus bn, I mean, these are important laws that we need to be familiar with because we need them at some point. We could have problems that we want to solve and we just need to break them down. Okay, so you see the addition part, subtraction, multiplication, multiplication of sequences, multiplication with this constant or a scalar. We see division and we see the power. Okay, so these are laws that are applicable. Now, there's even another powerful theorem. We're going to write the theorem and then we'll go into examples fully. Okay, so let me give you this other theorem. Now, this other theorem is very powerful, guys. It's called the squeeze theorem. In some other textbooks, they call it the sandwich theorem. Okay, so think about your sandwich. All right, so well here, Stewart book refers it also as the squeeze theorem. What is the statement of the theorem? Let's also have a sequence, of course, an infinite sequence, AN. Let's have another one we call BN. And let's have one more. Okay, we'll call it CN. Let these guys be sequences. Right? Suppose let me use the word assume. Assume that the limits of this guy, AN, and the limits of CN as n goes arbitrarily large. Suppose they give you the same limits, okay? Now, if after some numbers, let's call the number n0. This is n sub 0. We have, suppose we have this guy. So for every theorem, there's always a statement of a theorem and then a conclusion. Then what happens? Okay, so now let me explain. Let me explain intuitively what the squeeze theorem does. All right, so look at this guy. Look at this red box. I have AN less than or equal to BN less than or equal to CN. These are sequences. Now, if the limit of this guy as n goes large, if it gives me L. Now, and the limit of this guy, now these two guys are the extreme, right? If the limit of this guy as n goes large, the limit of this guy also as n goes large, if it gives me the same L, what happens? Remember, we have AN less than or equal to BN less than or equal to CN. The two extreme approaches the same limit. What does it tell me about the guy in the middle, guys? It only speaks one language about that guy. It means this guy would also converge to L. Okay, so now let me draw it in a different structure, but the same, I'm speaking the same language. This guy, remember, approaches L as n goes large. This guy approaches L as n goes large. What does it say about the one in the middle? By the sandwich theorem, this guy must go to the same L as n goes large. It's a very powerful one, guys, and it's one that you really must, if there's one of those theorems that you must know after studying this class, it is the squeeze theorem. It's such a powerful theorem. Okay. Another theorem. Remember, we're building the foundation. Chapter 11 is going to be a long ride. And if you're missing it from this session 1, if you're missing it from 11.1, then there's going to be a problem. Okay. So that's why I'm taking my time, trying to take it slow and then make sure you understand what is going on. Okay. Okay, theorem. Now, if the limit as n goes large of the absolute value of that sequence is 0, Now, these sort of theorems are applicable for alternating sequences, okay, because you need the absolute value to capture the negative part to take it out for you. So then the limit as n goes large of this guy gives me 0. Okay, that means that if the limit of absolute value, if the limit of absolute value of a sequence is 0, that means that the limit of that sequence itself is 0. Okay, now, but this is not the other way around. Okay, if this happens, that happens. But if this guy, it does not necessarily mean that this guy will be 0. Okay, so don't twist it, guys. These guys, some of these theorems are not if and only if. They are only in one direction. If this guy is 0, then this happens. But it doesn't mean that if this guy is 0, then this must happen. Okay. We'll see a lot of that when we do series. When we study series, you will see why those things are not like direct consequences of themselves. Okay, so let's do some examples of set theorem. So it looks boring. So let's do example. Limit, we want to find the limits as n goes large for 2n over n plus 3. I mean, who remembers Calc 1 here? How to compute your limits. Okay, so in this case, what do you do? When they have the same power, okay, when n, the highest power of n on the top is 1, the highest power of n on the bottom is 1. So what do you do? How do you compute such kind of limits? This is 2n over n plus 3. What do you do, guys? If you remember, you divide by that highest power of n. That essentially means that this is limit as n goes large is 2n over n divided by n over n plus 3 over n. Limit as n goes large, this is 2. I mean, this is just limit. If you forget this, you might have to do some, some reviews on limits. So this is divided by, this is 1 plus 3 over n. Okay, now, do you guys remember the limit laws? Remember, it applies to division. So now I'm going to apply that law. See, this guy's limit as n goes large, 2, divided by the limit as n goes to infinity of 1 plus 3 over n. What is the limit of a constant? It's just a constant, 2. Now, as n goes large, this guy approaches 0. So you have 1 plus 0 on the bottom, and this is 2. So that means the limit of this guy is exactly 2. Okay? Let's do another example. Now, in this example, we want to answer the question, is the sequence an equals n squared over n plus square root of 3n cubed convergent or divergent? Now, what do I do? If it converges, remember, by definition, the limit has to be finite. If it diverges, the limit has to be infinite or does not exist, right? Solution. So that means I'm supposed to investigate what this guy is going to be in the end, right? This guy. Now, how do you do this? Again, when you compute limit, you don't just plug in infinity. That would be wrong. You try to simplify this guy, okay? I have to find a way to simplify it. So, and to do that, my knowledge of limits, you have to divide by the highest power of n. And it turns out to be that the highest power of n in this case is n squared, not n cubed, guys, because this n cubed is under the square roots, okay? So it's n squared. So you do n squared divided by n squared, all divided by, you got an n squared here, I mean n, not n squared. You got n over there, divided by n squared plus. Now, when n squared gets into the square roots, what happens? It becomes n to the 4th. 3n cubed divided by n to the fourth. Okay, now let's see, this guy becomes limit as n goes large. You have 1 on the top divided by 1 over n plus square root of 3 over n. Now this is division, right? I can still apply the limit law. Limit as n goes large of 1 divided by the limit as n goes large. This is 1 over n plus square root of 3 over n. Limit of a constant is a constant. You have 1 on the top, right? So divided by. Now, as n goes large, this guy goes to 0. This guy goes to 0. So you have 1 over 0. And this is what? Undefined. So what's our conclusion, guys? It diverges. It's divergent. Okay. I hope it's all making sense right now. All right. Okay, so let's move on. We have a lot to learn because this is the foundation. We have to set it right. Another example, find the limits as n goes large of ln of n over n. Now, ln of n is a function. So we saw a theorem the other time that had to do with function. So how do we approach this, guys? Now, limit as n goes large of ln of n over n. You got to watch what I want to do right now. I can rewrite this guy in terms of x. So this is going to be like s goes to infinity, ln of x over x. Now, be warned, guys, you cannot do L'Hopital's rule for sequences, okay? So keep that in mind when you say, okay, if I plug in infinity, I have infinity over infinity, let me just do L'Hopital's rule. You cannot do that for sequences. You can only do that. That rule only applies to functions, okay? This is what I mean. This guy, I hope you guys remember this from Calc 1. Don't use this guy for sequences, okay? Not for sequences, but for functions. Okay, now this guy, let me start here. Now, what am I doing here? I'm converting a sequence to a function. This is correct. This is true. So now this guy is a function now, not a sequence. Since it's a function, I can now apply my L'Hopital's rule. If I plug in infinity, I have infinity over infinity. So I need to plug in by L'Hopital's rule. That means you differentiate the top, right? This is x goes large. Take derivative of ln of x, you have 1 over x. Differentiate the bottom, you have 1. All right, so as x goes to infinity, you even have a 0 divided by 1, which is what? 0. So what's going to be, if the question is about convergent or divergent, what do you say? This converges. I hope this makes sense. So let's say another one, this is the beauty of it. We see how we apply these theorems we stated above. Okay, so we want to find these limits. Now, this is an alternating guy, right? Remember, there was one of those theorems where we had the fact that if the limits, okay, so let me show you guys a second. Sorry, I'm flipping this across your faces. Now, this is it, guys. If this limit, right, equals 0, then this is 0. So that means it is even okay to check. Okay, what do I need to check? Check the limits of this guy for the absolute value of this guy. If it gives me 0, that means this answer, this guy is going to be a 0. Okay, but if it doesn't give me a 0, that doesn't actually mean that this guy would whether be a 0 or not. You don't know. Okay. So what does this absolute value help you do? It helps you to capture this negative part. So this is limit. And of course, this guy is just 1. It's large of 1 over n. As n goes large, what does this give us? This is 0. The theorem says if it gives you 0, then what's your conclusion? Then the original question is just going to be 0. Okay, so when you have alternating sequence, you can use that theorem. It comes in handy. Okay, I hope it's all making sense, guys. Now let's see another theorem. Now, if the limit of a sequence is L, and the function is, and suppose we have a function, suppose the function f is continuous at that limit L, then what happens? Then the limit as n goes large of f of an equals L. Okay, it's all going to be interesting now when we do an example, guys. Okay, at the level of the theorem, it's like, oh, what's going on? I understand. Okay, I know how you feel, but right now we have to see what to do. Okay. All right, so example, find the limit as n goes large of cosine of pi over n. Okay, so we want to find this limit. All right, so what do we do? What do we do? Let's see. Solution. Now remember that this guy is my an. So let an equals pi over n. Now, this theorem says that if the limit is L, so that means I have to find the limit of an. What is the limit as n goes large of pi over n? This is 0. Now, this first part of the theorem is ticked. Now it says, and if the function is continuous, and if the function is continuous at L, now is cosine of pi over n continuous at 0? The answer is yes. Okay, so I'll just say let f of x be equal to cosine of x. Okay, so this guy is actually continuous at x equals 0. I mean, this is Calc 1, the idea of continuity. So what happens by that theorem? That means that by the theorem, that means that the limit of this guy is just going to be cosine of the limit. Okay, so this is a new thing we're seeing now because we've not seen it in other examples that we did, where there can be this sort of, interwovenness. Okay, there can be this sort of interwovenness. So what do we do here? This guy is my an. I identify my an, find the limit of your an, it gives you 0. The next question is that function continuous at that point? Is it continuous at that limit? Yes, it is. So then you can find the limit of the original thing. Okay, so, and there can be this sort of limit operator moving in. When it moves in, you have a cosine of 0, and then you have 1. Such a beautiful thing. And in fact, if you can try this with a maybe on your computer with a graphic calculator or something, if you sketch this guy, if you sketch the graph of this guy, you will see that it's going to approach 1. Okay, that's the beauty of these things that we're learning. There's always this representation it does have. Okay, so let's look at another one, just a couple of more examples, and then that's going to be it. Okay, so the limit as n goes large of 2 to the power of n divided by 3 to the power of n plus 1. Now, how do you handle this? Okay, pay attention, guys. So limit as n goes large, 2 to the power of n divided by 3 to the power of n plus 1. I need to start by rewriting. So this guy is 3 to the n divided by 3 to the n times 3 to the 1, right? Laws of indices. I can pull out my 1/3. This is limit as n goes large, 2 to the power of n divided by 3 to the power of n. What do I know, guys? They have the same power. So I can still do some kind of algebra. This is 1/3. Limit as n goes large, 2 over 3 to the power of n. Now think about this. You have a small number and you are raising a small number to a large number. Okay, example is this. You have 0.05. You are doing 0.05 to the power of 1 million. What happens is even going to be much more smaller. Okay, it's even going to be much more smaller. So that means this limit goes to 0. 1/3 times 0 is just 0. So what do we conclude, guys? Converges. Okay, take note, guys, that when you run into this situation, when you have a small number and you're raising it to a large number, it even goes further down to 0. Okay, it even plunges down a lot more. Okay, so I think just let me see what else I might want to talk about right now. Okay, so I think I covered some very beautiful examples. I want to see if I find other examples I like to, to discuss with you guys. Looking at a nice example, because I try to pick examples, different examples that gives idea of a couple of things. Okay, so let me give an example that looks like this one I just did. Okay. E to the n over 3 to the n. Okay, so this guy is just almost the same thing we just did some moments ago. What happens? This guy goes to 0. Okay, it's a small number, rose it to a very huge number. 0. Okay, so another one was large of this guy. Now you saw that we had a theorem that says when we have this alternating guy, we need to deal with it in the level of in another level. Okay, so let's check. If this guy gives, I check the limit with respect to the absolute value. Okay. Then I'm left with square root of n. What is this limit, guys? It's infinity. So that means that this original guy, so that means that that guy is divergent. Okay. So, okay. This guy, now let me write it. Let me use the other definition to write it so that you can know we can write it in different ways. That means this guy approaches infinity as n goes large. So what do we conclude? Divergence. So, I mean, this is the beauty of all of this. This is the beauty of how we deal with them and how we relate with them. Okay. I hope this all makes sense. All right. So I hope you practice more questions and then see